Okay, well, welcome everyone to another TCS Plus talk. It's really a great pleasure to have Victor Reis today, who's going to tell us about the subspace flatness conjecture and fast integer programming. And just before we begin, I do want to encourage everybody to keep their cameras on. It gives Victor some visual feedback. It makes giving TCS Plus talks more fun and engaging. And after the talk, we're recording this for our YouTube channel. After the talk, there will be an unrecorded session where we can just hang out and keep asking questions and so on. And then before we begin, I will say that TCS Plus is a large effort, so I'd like to thank the rest of the organizers. These are Clement Kannan, Rachel Cummings, Anindya Day, Sumega Garg, Gadam Kamath, Ilya Rajinstein, Oded Regev, Salil Shram, Noah Stephens-Davidowitz, Thomas Vidik, and David Weiss. And I will say that we're always looking for more suggestions. If you think there's a great result or a great talk that you'd like to see be part of TCS Plus, please send us a pointer, and we're always looking for suggestions. But okay, with that being said, I'll hand the floor over to Victor, and please take it away.
Yeah, thanks, Eric, for the introduction, and thanks, Clement, for the invitation. I'll be talking about some joint work I did this year with my advisor, Thomas, from my PhD. So So the main object of study we're going to look at is lattices. So lattices are discrete subgroups of Rn, which are defined by some basis B. So B is a matrix of linearly independent columns. Here's an example in 2 dimensions. And a lattice can have multiple bases. So here's one of them. And here, here's the determinant of the lattice, which is a measure of the sparsity of how sparse the lattice is. It's like the area of this parallelogram in the picture. But it can have more than one basis. Like, all of these parallelograms will have the same volume as long as they span the lattice. And a useful property is that if you translate this parallelogram over the entire space, this will tile everything. It is essentially like you can round down if you have a point, you can take the fractional part and you can translate by this basis. So we're going to be looking at a quantity related to lattices called the covering radius. So the covering radius is the following. So given a convex body K, so imagine, for example, this one, it's the minimum radius so that if I put a copy of K in every point of the lattice, it will cover the entire space. And alternatively, there's another way of thinking about this. It's the minimum radius so that no matter where I put the convex body, it will intersect the lattice. For example, here, I need to scale it by this much. And then no matter where I put it, there will always be a point in the intersection of the convex body and the lattice where I need to translate. So this quantity is like a little hard to compute. Like it's not clear how you would, given a convex body K and a lattice L, like how would you actually compute this quantity? So we're going to be looking instead at ways of approximating it. And we're going to start by thinking about lower bounds that we can get for the covering radius. So one useful property is the following. So if I cover the entire space by putting copies in the lattice points, the volume of this body needs to be at least the determinant of the lattice. So recall the determinant of the lattice was this area of this parallelepiped. It measures how sparse the lattice is. And so this corollary will follow directly from the previous sentence. So let's first try to understand why this first sentence holds. So if I take a volume of a convex body, it's just the integral of the indicator function over this convex body. And I can write this as a union of these fundamental parallelepipeds because Rn can be written as a union of all these translates of these parallelepipeds. So I can write it in the following way. And by the assumption that I'm covering the entire lattice, this quantity in the sum is always at least 1. So this is measuring how many points there are in the translate of the convex body. And by the assumption that I'm always covering the space, this will be at least 1. So this is at least the volume of the parallelepiped, which is the determinant of the lattice. And so if you think about what L plus K equals Rn means, it means that the covering radius of the convex body is at most 1. So by some scaling, we can get the corollary. So it's essentially saying, if the radius I'm scaling by is not large enough, then the volume won't be large enough, and therefore I'm not covering the entire space. So this corollary is just a rescaling and normalization of the previous slide. So if this wasn't too clear, let me give you a picture. So I have my lattice. I have some bases in the area of the blue parallelograms, the determinant. And I have some convex body K. In this case, it's just an ellipsoid, an ellipse in this case. And this lower bound that I explained in the previous slide is just saying that the covering radius is at least this determinant over volume normalized. So if you try to apply this lower bound for this setting, well, you're going to get something that looks like this. Well, there's a lot of overlap, and you're actually not quite at the covering radius yet, meaning that this lower bound is not tight in this case. And an observation that was made by Kannan and Lovász is that there's a way to make this lower bound better by, instead of applying this lower bound to the entire space, we can think about projecting everything onto a subspace first and then applying this lower bound. So what does this mean? So it means the following. Imagine I take this blue line W here, and instead of applying this lower bound on the covering radius for the original body K and the lattice L, I will first project everything onto this blue line. So what does this mean? It means, okay, so imagine if I'm covering the entire space. After I project, I'm still covering the blue line. This is just by linearity of the projection. That's in this the second line here. And therefore, it means that, if I want to cover this blue line, well, it suffices to cover the original space. And I get this lower bound just by applying the same reasoning from before. So for any subspace W, we have such a lower bound. So this was first noted by Kannan and Lovász in their paper in the 80s. And the best possible lower bound of this form, we call this Kannan-Lovász lower bound, so mu KL for Kannan-Lovász, not to confuse with the lattice L and the convex body K. Just happens to be the same initials. And what they also showed in their paper is that this is a good approximation in the sense that this lower bound is tight up to a factor of n. So for any convex body K in any lattice L, this lower bound that I described is tied up to a factor of n. Which might be a little surprising, like the original lower bound they described that was not projecting onto any subspace, that can be arbitrarily bad. So that does not have any dependence on the dimension. But if you actually restrict to a subspace, they show that you have this finite approximation for any fixed dimension. And about 10 years ago, Dadush conjectured that you can do much better. So his conjecture is that actually just a log factor suffices, which would be tight, because in the Kannan-Lovász paper, they provided this example of some simplex for which, there is some kind of, there's a gap between this lower bound and this covering radius of log n. So Daniel went a little further, and he actually conjectured that this is always the worst case. And so why did Daniel care about this? Well, he showed that also if you have such an improved bound, then you have a faster algorithm for integer programming, which I'll describe in a second. But that was the main motivation for his work. So what we showed is that this conjecture is almost true. Well, we show that it's true up to a factor, well, an exponent in this log. So what we showed is that it's true up to a log cubed n. That any lattice L and any convex body, this covering radius can be approximated up to this log cubed by this lower bound of Kannan and Lovász. And following Daniel's work, we show that we just essentially we use his work and we show how to compute the subspace that achieves this log cubed. And we get as a corollary that, you know, we can always solve integer programs, meaning you can, given a convex body K, we can find a point in the intersection of the integers in K, or tell that no such point exists in time that's like log n to the 4n. So, you know, it's a constant times n. And this problem was studied for a long time. Well, we know it's like NP hard because, for example, like the 3-sat problem can be written as an integer program. So, you know, we can't do better than 2 to the n, like assuming the exponential time hypothesis, but there has been a lot of work since the 80s improving this runtime by Lenstra, Kannan, and Daniel Dadush. So previously the bound on this Kannan and Lovász, like the approximation factor was n, which by Daniel's work, it implied an n to the n algorithm for integer programming. And so since we improved this to a log cubed, we get a log n to the order n. Well, there's another log in there because we need to actually compute the subspace and not just show one exists. So, you know, yeah, so I'll just give a couple other corollaries of this result before I explain what's happening. So a couple corollaries are the following. So here I'm saying that any asymmetric convex body can be essentially approximated by a symmetric convex body up to a polylog. So now if I want to measure what's the covering radius of my body K, I can just look at my body K minus K instead, up to this log cubed factor. And this follows from the previous theorem plus some volumetric estimates for this difference body. Another corollary is that the so-called flatness constant in dimension n, we have a better bound for it. Previously was known to be n to the 4/3 up to some polylogs. And so what does this mean? The picture is the following. This is basically a mathematical statement that, you know, if I have a convex body that does not intersect the integers like this K in the picture, then it can be like kind of like covered, or like there's like a finite number of hyperplanes that stab this body. So, you know, like if you have you want to pick the best direction C, there's an integer direction, so that few hyperplanes will cover this body. In this case, there's like 4 hyperplanes. And the claim is that, you know, it's a nearly linear number of hyperplanes suffice. This is also a corollary of our main theorem. So first, I'll give an overview of what Daniel's algorithm is doing. So here we'll solve the more general problem of, given the convex body K and the lattice L, determine whether there's a point in the lattice that is also in K. It's pretty much the same thing because, you know, you could serve the integers and apply some linear transformation and you get any lattice. So his algorithm is the following. So first, if K is gigantic, so like imagine if K is very large, we want to be able to shrink K. So that's the first step here. Well, in this case, in the picture, we won't need to do that. But, you know, it's just a way for us to not do too much work. Like if we have some way of approximating the covering radius and we can shrink it, we do that. And then we find some subspace W that approximately attains this lower bound. And the point here is that we are able to, like if we have any integer point inside K, when you project this point into W, it's still a lattice point. So the picture is as following. So if I project K onto W, any integer point, so it's like you can see there's one integer point in the picture here. When it projects onto W, it's still one of these dark blue points. You know, obviously there could be other dark blue points that don't correspond to any integer point inside K, but, you know, if there's any, it has to be one of those. And then what we do is we recurse on these lower dimensional problems that correspond to these fibers of this projection, meaning like all the set of points that project to the same point. And so the idea here is that Daniel showed that if you have this good approximation to the covering radius, then you actually don't need to recurse on too many points. So there's this X here, which corresponds to the set of all these dark blue points. The size of it is upper bounded. So more specifically, the analysis is like at a high level is as follows. first we can compute this subspace W in time 2 to the order n. There's also a work of Daniel from 2019. Then we can use this covering radius guarantee. I'll give a little more detail later how do we do this, but we can essentially upper bound how many points we have in this, how many dark blue points we have to recurse on. And we can also enumerate all of them in this time. So not only is there a bound on their sides, we can also explicitly write them down in this time. And then it's just a simple recursion to compute the runtime of the algorithm. So T of n is the runtime for dimension n. We compute the subspace in time 2 to the n. And there's like these log to the 4D and many subproblems, one corresponding to each point inside X. Each of them will take time T of n minus D, because I have to recurse on this fiber, on this gray fiber in the picture. So if you solve this, you get the runtime is log n to the order n. I won't go into the full analysis of this. I just want to give an idea of how you can bound this number of points. And Daniel's theorem is as follows, that if you have any lattice in any convex body P, so P corresponds to the projection of K in the subspace W, we can upper bound this how many points there are based on this ratio of volume and determinant. And if you use our main theorem, we can upper bound this quantity in terms of polynomial log. And you just do some math and you can show that the number of points at most log n to the 4D. I won't get into too much detail how he proved this theorem, but that's the high level idea, that you can upper bound how many points you're recursing on. Cool. So now I want to change gears and like actually give you some flavor of how we proved our main theorem. I'll give you a sketch of how we proved this approximation guarantee. And first, I'll give you a one slide summary of the proof that probably won't make too much sense. But here's if you don't remember, here's the full theorem again. So you have this lower bound on the covering radius based on the subspace. And the claim is that it's tied up to this log cubed vector. So the high level idea is the following. First, we're going to put K in some well-rounded position. So, like K might be very thin and very ill-behaved. First, we're going to apply some linear transformation that puts K in some nice position that I'll talk about later. And that will also change the lattice, but importantly, it won't change the ratio of determinant versus volume, because we're applying the same linear transformation to both the lattice L and the body K. And then we're going to apply a kind of triangle inequality to this covering radius. So we're going to split the problem into a section of a subspace and a projection onto its orthogonal complement. So we're going to split the problem into two parts. And so the point of doing this is that the second part here is actually easy by induction, because if you have a projection of a projection, well, that's still a projection. So that's easy. But the hard part turns out to be analyzing this section. So this part is the tricky part. And to deal with it, we will have to pick, we call it like a nice chain of lattices that is one contained in the other. And we take the subspace U that we're recursing on to be some prefix of this chain. So that was like the one slide summary of the proof that probably didn't make too much sense. And now I'll go deeper into the first part and then the second and third. So the first part is the following. So there's, given a convex body K, we're going to define this function L of K to be the average norm of a Gaussian with respect to the convex body. If you'd rather, you don't have to think about this as square in power of 1/2. You can just think about the average norm. So this is like the average thinness of my convex body. So the norm is like how much you have to scale K until X is contained inside the body. So we want to know what is the average norm of a Gaussian. And the point here is that we want to pick some linear transformation to put K in a nice position so that both this L value of the original body K and the L value of its polar, which is something you get by replacing the vertices by constraints and vice versa, like in the picture, we want both of these quantities to be small. It's possible that they start out being extremely large. Like in this picture, you could have like very skinny bodies that won't behave very well in this L norm, in this L function. But we want their product to be small. So there's a theorem that does this due to Figiel, Tomczak, Jagerman, and PCA. That essentially says that for any symmetric convex body K, well, it has to be symmetric. We don't know if this is true for general convex bodies yet, but at least for symmetric, this works. That there is an invertible linear map that you can always put K in a nice position, TK, that is kind of like similar to what you would get for the unit ball. Meaning, if K was the Euclidean ball, you'd get a product of N, because the average norm of a Gaussian with respect to the L2 norm, the usual Euclidean distance, the average norm of a Gaussian is square root N, and the polar is the same for the unit ball. So then you'd get like square root N times square root N, which is N. But here, we're saying that for any convex body K that's symmetric, we can always get pretty close to the ball. So, we only pay this log factor extra on top of it. So this is a pretty deep result. And we call this like the L position. So I won't go into detail of how they prove this, but it's a nice tool in general for high-dimensional geometry problems. So another useful thing about this L position is that we can relate it to this. So this is the L position in this case. So, start like this, and then you make it a nice position like this. So another nice thing about it is that we can relate it to the mean width of the convex body. So this is a little different. So, here we take some direction theta, that's just a unit vector in the, norm 1. And then I consider what's the average value of this width in this direction. So here, this inner product is just like the width in this direction, theta. And there's a theorem due to Urison that, if I have a fixed volume, then the body that minimizes this mean width is just the Euclidean ball. So another way of saying this, because it turns out that this mean width is actually related to the L function of the polar. So, you can rewrite this in a normalized way that says, if I have any convex body K, its width must be at least as large as this normalized volume of the body with respect to the unit ball. And another way of saying this is that, the L value of the polar turns out to be up to a square root N factor, the same thing as the mean width, if you just write down the definition. And this means that we can upper bound the volume of the body up to this up to 1 over N times this L value of the polar. So this 1 over N comes from both the square root N factor that you lose from the Gaussian, and also from this volume of the Euclidean ball. So the volume of the Euclidean ball turns out to be around N to the minus N over 2. So if you rearrange this, you get this 1 over N factor up to a constant. So this is just a nice way of relating the volume to this L value. And we're also going to have to think about how can we put not just the body, but also the lattice in like a nice position. But this turns out to be a little more subtle. So here, I define this stable to be lattice. I define this lattice to be stable if the determinant is 1 and all the sub-lattices have determinant at least 1. So a sub-lattice is just what you get when you intersect the lattice with the subspace. And, I kind of want that all directions are evenly spread in some way. I don't want any direction to be too dense. So for example, here Z squared is a stable lattice. And in order to talk about this chain of that I alluded to before, we're going to have to define this quotient lattice. So here, the picture is the following. I have some sublattice L prime. And I project the orthogonal complement. I projected the original lattice onto the orthogonal complement of L prime, and that I call the quotient of the lattice. It turns out that this quotient has a lot of nice properties. For example, like the determinant of L is equal to the determinant of L prime times the determinant of L quotient L prime. So essentially, it's a way to factor the lattice into well-behaved parts. And then so the thing we're going to try to do is, okay, I have a lattice that I end up with. Originally I had, maybe I can think of, I started with the integers. I applied this L position transformation. I ended up with some crazy looking lattice. And I want to get some control over how it looks like. And the way we're going to do this is by this so-called canonical filtration. So this definition is a little subtle. If this is the first time you've seen it, the point is the following. So I plot all my sublattices onto this 2D plane, where in the x-coordinate, I put the rank of the sublattice. And in the y-coordinate, I put the log determinant of the sublattice. So I have infinitely many lattices that I plotted here, but I take their upper convex hull. So I end up with this chain L0, L1 up to Lk corresponding to the vertices of this upper convex hull. A priori, it doesn't make a lot of why would you want to consider this plot? But it turns out that this is a very useful plot. In particular, it has these three properties that I'm listing here. That if you look at these vertices, one is actually contained in the next one as lattices. So that's not so clear from this definition that I gave you. But it's true that the lattice is contained in the next one. And by the picture, all these normalized determinants of these quotients are increasing. Oh, that's just because the slopes of any convex hull, any upper convex hull are increasing. So you can see that these slopes are increasing. Therefore, these normalized determinants are also increasing. And moreover, what's interesting is that all of these quotients are also semi-stable, meaning that they're a multiple of a scalar multiple of a stable lattice. Like this, if you divide by the normalized determinant, they will be stable. And recall that stable means that every sublattice of it will have large determinant, at least one. So what does this mean? In a high level, it means, okay, I started with some lattice L. I can create this chain that kind of splits the lattice into nice chunks in terms of these quotients. It's kind of like a prime factorization, but not really. It's more like, if you study group theory, you can think about it as, if you have a simple group decomposition, it's kind of similar to that. So essentially, I want to have some control over how this lattice looks like. Well, one way to do this is by looking at these quotients, which are guaranteed to be stable. Okay, so we're gonna look at, okay, how can we actually bound this covering radius? So first we assume that it's symmetric for now. Then I have a slide later on explaining how to remove this assumption. But then, so first of all, we're going to apply this linear transformation K, T to K, so that, I want to put in this L position that's almost like a ball. And then I want to find the subspace subspace U so that I can recurse on U and on the projection on the orthogonal complement of U. And as I mentioned, the hard part is dealing with this section. So here the claim is the following: if I have a symmetric convex body K, and for any lattice, there's some subspace of dimension at least half of the full dimension, which has this bounded covering radius up to a log squared, actually. And the full result will just follow by a simple induction. I'll get to later. So here's the idea. We're going to take this canonical filtration from the previous slide, and we're going to define these Ri's to be these normalized determinants of these quotients. They're increasing. And another trick we're going to have to do is we're going to have to group similar values of Ri together. So instead of taking the entire canonical filtration, we're actually going to take a subsequence of it in such a way that this Ri's are actually increasing pretty quickly. So, these Ri's are increasing, but, I want that they're not only increasing, but also increasing exponentially. So I just take a subsequence of this canonical filtration to do this. But we will lose some of the nice properties, but only approximately. And then we're going to take the first index for which the dimension of this prefix is at least half. And then we're going to take this U to be this the span of this prefix. So the picture is the following. I have my canonical filtration here. I mark the midpoint n over 2. And I take the first index, which is at least n over 2. So I take this to be my subspace U. And so recall that like in the Kannan and Lovász lower bound, we were projecting onto some subspace. Well, that we will take to be the suffix corresponding to it that's also at least n over 2 in size. So it's like if you go from the other endpoint and you want to dimension at least n over 2, that's your W. Okay, so like how can we bound these covering radius? So the first thing we're going to have to do is we apply this triangle inequality of sorts to this covering radius intersected with the subspace U. So recall that U is everything up to I star. So in this summation, I'm having everything from index 1 to I star of this covering radius of this quotient. And then I have this scary looking convex body here, which is a projection of a section, which looks not very useful. But then we're going to use some tools about the L function that are going to be very helpful for us. So the main tool, so here the nice thing about this inequality is that these quotients are stable by the property of the canonical filtration. And so we need a tool to deal with covering radii of stable lattices. And this is coming from a work of Noah, who's in the audience here, and also Oded Regev. And they show this thing called this Reverse Minkowski Theorem, which is a very powerful tool, which unfortunately I won't have too much time to get into. But we couple these tools with also some transference theorems of Banashzik to guarantee this covering radius upper bound for stable lattices. So here we're saying that for any symmetric convex body K and any stable lattice L, we have this upper bound up to a log factor in terms of the L value of the convex body. So this theorem is actually quite deep. It takes a lot of different tools to get to this. So I won't go into the proof. But then we also need a tool to get rid of this projection and this intersection. It turns out to be a lot simpler, actually. It turns out that just by a convexity argument, you can argue that this L value is upper bounded by the L value of the original body. So this one is actually quite simple. And then if you put these two lemmas together with the inequality above, you just get the following. You get the covering radius of this section is bounded by log n times this L value of the body times this normalization factors, which are the RIs of each quotient in the sum. So now we kind of reduce the problem to, okay, we want to upper bound the covering radius. How do we upper bound these normalized determinants? And here the idea is the following. So I take this subspace W that I alluded to before, which is a suffix, and I call D the dimension. And I simply upper bound the normalized determinant by this determinant of this projection of L onto W, which corresponds to a geometric average of all the normalized determinants at least I star. So this is just this inequality here is just saying that Ri star is upper bounded by geometric average of all the normalized determinants larger than it. And then, so this is kind of start looking like the Kannan and Lovász lower bound. And then I essentially multiply and divide by the same number, which is the volume, so that it looks even more like the Kannan and Lovász lower bound. Now I just need to upper bound this volume here. And for this, I use the Urison inequality that I alluded to in the previous slide. And it says that the normalized volume of this projection is bounded by the L value of the polar of this projection. It turns out the polar of this projection is actually the section with this polar body. And I use the previous lemma to upper bound the section by the original L value. So in the slide, what we did is essentially I took the normalized determinant Ri star and I upper bounded it by the L value of the polar up to a factor of 1 over d times this Kannan and Lovász lower bound that we wanted to consider. So now we just have to put everything together. So recall we had this inequality here. And by the grouping that we made, so we're not considering the entire canonical filtration, we take these jumps so that the RIs are exponentially increasing, which means that this entire sum is bounded by the largest term up to a constant factor. You know, if you think about like the part of 2, 1, 2, 4, 8, 16, well, that's almost like 32. Like it's only a factor of 2 away from the largest term. So this means that we only have to bound the largest term. And in the previous slide, we did that. We bounded it by the L value of the polar over d. And by the position that we chose for the convex body, we have an upper bound on this L times L polar of n log n. And moreover, by the choice of the subspace that we made, like we chose the U to be the least one so that the dimension is at least n over 2. So W also has dimension at least n over 2, which means that this fraction of n over d is at most a constant, the most 2. So we got essentially we got a log squared from this slide. Okay, so putting everything together, so what do we get? So far we've shown that for symmetric convex bodies, so let's see where this log cubed comes from. So first we put this k in the null position so that the product of the L and L stars at most n log n. We use this triangle inequality, and by induction, the second term is actually quite easy. We just pay log cubed of n over 2 because the dimension of U perp is at most n over 2. The first term is what we did in the previous slide, and we pay the log squared factor for it. And we just have to notice that, the log squared plus log cubed of n over 2, that's at most log cubed in base 2, I guess. So that's the full proof of the symmetric case. I guess there are a few lemmas that I didn't get to, but that's the sketch of the proof of the symmetric case. And recall that we needed to assume that it's symmetric because, in order to put k in this L position, so far we only know how to do this for symmetric convex bodies. It's still a conjecture of, can you actually put any convex body in an L position that's like n times polylog n? We're not sure. But, at least for symmetric convex bodies, we can do this. And then we need to pull out some other geometric hammers to cover the non-symmetric case. So I won't go too deep into that. I'll just give you one slide of what it looks like. So here's the proposition we had before for symmetric convex bodies. It turns out that it's also true for general convex bodies. And the way we do this is we eventually had the point where we needed to bound the volume of the projection of the convex body. So essentially what we're going to do is we're going to replace k by a symmetric body. So it's going to be this k intersect minus k. So it's like a symmetrized version of k. But it's also smaller. So, there's some work that we need to do because we're upper bounding the covering radius by the covering radius of the smaller body, k sim, which is k intersect minus k. And then we actually need to upper bound the volume of the projection in terms of the volume of the projection of this intersection, which is a smaller thing a priori. So this actually took us some time. And fortunately, there's a theorem of Beatrice Vrizio that she actually did this. Essentially, she showed that, if you put this convex body K so that the barycenter is at the origin, then you actually have a pretty decent upper bound on the volume of the projection of K in terms of the volume of the projection of the symmetrized body, which pays this n over d to the 6, but d is gonna be like n over 2 in this case for our setting. So it turns out to be just a constant that we're losing here. You know, in the first version on the archive of our paper, we actually didn't know how to do this with the barycenter at the origin. We actually had this other point called the centalo point, which we moved to the origin, but it turns out barycenter is just a much nicer point, and Fabrizio had this very nice theorem. Okay, so I'll just leave you guys with one open problem. That's pretty fascinating. You know, we solved integer programs in time log n to the order n, but as far as we can tell, it's very possible that, you know, we could do this in simply exponential time. We just have no idea how. Okay, thanks.
Thanks, Victor, for the talk. Are there any questions from the audience? I guess I have a question about this last open problem. Is there a analogous like structural lemma that would let you get this in 2 to the O of n time? There's something that you believe to be true, or do you need a completely new algorithmic approach?
Yeah, so the subspace, like the approximation of the covering radius of Kannan and Lovász, it's known to be, there's at least a log n gap from a simplex that, you know, you cannot hope to get better than log n. So, you know, at least from this exact same approach, we don't have any idea of how to do this. And yeah, I guess so far we don't have any conjecture that would lead to this. You know, we don't even have like a certificate, you know, if you have like a non-deterministic Turing machine, like if you just, we don't have any certificate that, you know, would be able to provide such an algorithm.
Any other questions from the audience? If not, I can take us off the recording.